In this video lesson, we show how boundary integral equations may be derived for two-dimensional elastostatic deformations of homogeneous anisotropic materials, and how they may be applied to solve numerically two-dimensional elastostatic problems. We start with a quick look at some basic equations for elastostatic deformations of anisotropic materials. The generalized Hooke's law gives sigma ij equalsCijkp del uk over del xp. The Cartesian components of the displacement and the stress in the material under consideration are given by ui and sigma ij, respectively. The displacement and the stress are functions of the Cartesian coordinates x1, x2, and x3. The elastic moduli of the material are given by the Cartesian tensorCijkp. The lowercase Latin subscripts have values 1, 2, and 3. The Einsteinian summation convention applies for repeated lowercase Latin subscripts over 1, 2, and 3. The equilibrium equations are given by del sigma ij over del xj plus fi equals 0, where fi is the xi component of the body force acting on the material. The equilibrium equations can also be written in the integral form. Surface integral over del capital omega sigma ij nj d a plus volume integral over capital omega fi dv equals 0. Note that capital omega denotes the three-dimensional region occupied by the material. Del capital omega is the surface bounding the region capital omega, and ni is the xi component of the unit normal vector to the surface, del capital omega, pointing out of capital omega. The generalized Hooke's law, and the equilibrium equation, gives rise to the elliptic partial differential equations.Cijkp del 2 uk over del xj del xp plus fi equals 0. If the material is homogeneous, that is, if the elastic moduli of the material are constants. Consider now the case where the displacement components, uk, are functions of x1 and x2 only, and the body force components, fi, are 0, that is, the case of two-dimensional elastostatic deformations in the absence of body force. For this case, the elliptic partial differential equations governing the deformations become Ci1k1 del 2 uk over del x1 square plus Ci1k2 plus Ci2k1 del 2 uk over del x1 del x2 plus Ci2k2 del 2 uk over del x2 square equals 0. Let us look for solutions of the form uk equals ak times fx1 plus tau x2, where ak and tau are constants, and f is an arbitrary single variable function that is at least twice differentiable. Substituting into the partial differential equations, we obtain the following system of three homogeneous linear algebraic equations in three unknowns, ak Ci1k1 plus Ci1k2 plus Ci2k1 tau plus Ci2k2 tau square times ak equals 0. For non-trivial ak, the constant tau is required to satisfy. Determinant Ci1k1 plus Ci1k2 plus Ci2k1 tau plus Ci2k2 tau square equals 0. The equation. Determinant Ci1k1 plus Ci1k2 plus Ci2k1 tau plus Ci2k2 tau square equals 0. Is a sixth-order polynomial equation in tau. From physical considerations, the solutions of the polynomial equation can be shown to be complex numbers with non-zero imaginary parts, which occur in complex conjugate pairs. For more details, one may refer to Stroh, 1958, and Clements, 1981. Assume that the polynomial equation in tau has three distinct complex solutions, tau 1, tau 2, and tau 3, with positive imaginary parts. Let AK alpha be a non-trivial solution of the homogeneous linear algebraic equations in AK, corresponding to tau equals tau alpha, for alpha equals 1, 2, 3, that is, Ci1k1 plus, Ci1k2 plus Ci2k1, tau alpha, plus Ci2k2, tau alpha, square, AK alpha equals 0. No sum over repeated subscript alpha. Note that we use Greek subscripts to denote subscripts that are not associated with components of tensors. There is no summation over repeated Greek subscripts, unless explicitly stated otherwise. The solutions of the homogeneous elliptic linear partial differential equations can be written in the general form, UK equals, real part of, sum, alpha equals 1 to 3, AK alpha, F alpha, Z alpha. Note that, Z alpha equals x1 plus, tau alpha, x2 is a complex variable, and F alpha is an analytic complex function of Z alpha. From the generalized Hooke's law, the stress components, sigma ij, are given by, sigma ij equals, real part of, sum, alpha equals 1 to 3, Lij alpha, F alpha prime, Z alpha. Here, F alpha prime, Z alpha, denotes the first order derivative of F alpha, Z alpha, with respect to Z alpha. The constants, Lij alpha, are given by Lij alpha equals,Cijk1 plus tau alpha,Cijk2, AK alpha. It is easy to show that, Li1 alpha equals, minus tau alpha, times, Li2 alpha, a result that we will use later on. For a useful singular solution, take F alpha, Z alpha, equals, B, alpha, times, complex log, Z alpha minus C alpha, where B alpha, are constants, C alpha equals, Psi1 plus, tau alpha, Psi2, and Psi1, Psi2 is a given point, on the OX1x2 plane. Since AK alpha are complex constants, and the complex logarithmic function is multivalued, we must ensure that the displacement field, UK, is single-valued at all points, x1, x2, except at, Psi1, Psi2, where F alpha, Z alpha, is not well defined. That is, we choose the constants, B alpha, to satisfy. Integral, over C, duk equals, 0, for any simple closed curve, C, enclosing the point, Xi1, Xi2. From the singular solution, we find that, integral, over C, duk equals, real part of, sum, alpha equals 1 to 3, AK alpha, B, alpha, times, integral, over C, d over dz alpha, complex log, Z alpha minus C alpha, dz alpha, which equals, real part of, sum, alpha equals 1 to 3, AK alpha, B, alpha, times, integral, over C, dz alpha, over, Z alpha minus C alpha. Cauchy integral formula gives, integral, over C, dz alpha, over, Z alpha minus C alpha, equals 0, if, Xi1, Xi2, lies outside C, and, integral, over C, dz alpha, over, Z alpha minus C alpha, equals, 2 pi I, if, Xi1, Xi2, lies inside C, that is assigned a counterclockwise direction. Thus, We find that integral over c duk simplifies to 0 if xi1, xi2 lies outside c, and real part of sum alpha equals 1 to 3 ak alpha b alpha 2 pi I if xi1, xi2 lies inside c. So, for uk to be single-valued, we have to ensure that real part of sum alpha equals 1 to 3 ak alpha b alpha 2 pi I is equal to 0. If b alpha equals an alpha p dp, where dp are real constants, and n alpha p are constants such that sum alpha equals 1 to 3 ak alpha, and alpha p equals delta kp, Kronecker delta, then real part of sum alpha equals 1 to 3 ak alpha b alpha 2 pi I equals real part of 2 pi I delta kp dp, which is equal to 0 as required. The 3 by 3 matrices ak alpha and n alpha p are inverses of each other. If tau1, tau2 and tau3 are distinct, ak alpha is invertible, that is, the existence of an alpha p is guaranteed. One may refer to Clements, 1981, for the proof of this. Explicit formulas for tau1, tau2 and tau3, and the matrices ak alpha and an alpha p for particular transversely isotropic materials are given in Clements, 1981. For isotropic materials, tau1 equals tau2 equals tau3 equals I, and the matrix ak alpha is not invertible. However, the analysis here can be recovered for isotropic materials in a limiting sense by introducing a small perturbation in the isotropic elastic moduli, as explained in Ang, 2013. The displacement components, uk, here satisfy the elliptic partial differential equations for two-dimensional elastostatic deformations, with zero body force everywhere, except the point, psi1, psi2. For convenience, we can think of uk here as satisfying the elliptic partial differential equations for two-dimensional elastostatic deformations with body force, capital Fi equals Fi delta x1 minus I1, x2 minus I2, where Fi are constants and delta x1 minus I1, x2 minus I2 is the Dirac delta function centered about psi1, psi2. That is, we can think of uk here as satisfyingCijkp, del2, uk, over, del xj, del xp, equals, minus fi, delta, x1 minus I1, x2 minus I2. For details, refer to Stroh, 1958. Let C be a simple closed curve enclosing the point, psi1, psi2, and R be the two-dimensional region enclosed by C. The equilibrium equations in integral form give, real part of, sum, alpha equals 1 to 3, Lij alpha, and alpha p, dp, line integral, over C, nj, ds, over, z alpha minus c alpha, equals, minus fi, double integral, over R, delta, x1 minus I1, x2 minus I2, dA, which simplifies to, minus fi. Without loss of generality, let us take C to be the circle of center, xi1, xi2, and radius, rho. If we let x1 minus I1 equals rho cos theta, and x2 minus I2 equals rho sin theta, and use Li1 alpha equals minus tau alpha, Li2 alpha, we find that real part of, sum, alpha equals 1 to 3, Lij alpha, and alpha p, dp, integral, over c, nj, ds, over, z alpha minus c alpha. Equals, real part of, sum, alpha equals 1 to 3, Li2 alpha, and alpha p, dp, integral, theta equals 0 to theta equals 2 pi, sin theta minus, tau alpha, cos theta, over, cos theta plus, tau alpha, sin theta, d theta. Note that, n1 equals cos theta, and n2 equals sin theta, on the circle. The integral on the right-hand side of the equation here can be evaluated analytically to give minus 2 pi I for tau alpha that has positive imaginary part. Hence, the equilibrium equations relate the real constants, di and fi, by imaginary part of 2 pi, sum, alpha equals 1 to 3, Li2 alpha, and alpha p, dp equals minus fi. For the fundamental solution, we take the point force vector, F1, F2, F3, to be given, in turn, by the unit vectors, minus 1, 0, 0, 0, minus 1, 0, and 0, 0, minus 1. Take, F1, F2, F3 equals, minus 1, 0, 0, and 2 pi dp equals, capital dp1. To obtain capital phi k1, x1, x2, psi1, psi2 equals 1 over 2 pi, real part of, sum, alpha equals 1 to 3, ak alpha, and alpha p, dp1, complex log, x1 minus i1, plus, tau alpha, x2 minus i2. And imaginary part of, sum, alpha equals 1 to 3, Li2 alpha, and alpha p, capital dp1 equals, delta I1. Take, F1, F2, F3 equals, 0, minus 1, 0, and 2 pi dp equals, capital dp2, to obtain capital phi k2, x1, x2, psi1, psi2 equals, 1 over 2 pi, real part of, sum, alpha equals 1 to 3, ak alpha, and alpha p, dp2, complex log, x1 minus i1, plus, tau alpha, x2 minus i2. And imaginary part of, sum, alpha equals 1 to 3, Li2 alpha, and alpha p, capital dp2 equals, delta I2. Take, F1, F2, F3 equals, 0, 0, minus 1, and 2 pi dp equals, capital dp3, to obtain capital phi k3, x1, x2, psi1, psi2 equals, 1, over 2 pi, real part of, sum, alpha equals 1 to 3, ak alpha, and alpha p, dp3, complex log, x1 minus i1, plus, tau alpha, x2 minus i2. And imaginary part of, sum, alpha equals 1 to 3, Li2 alpha, and alpha p, capital dp3 equals, delta I3. We refer to capital phi kr, x1, x2, psi1, psi2 as the fundamental solution of the elliptic partial differential equations for two-dimensional elastostatic deformations. Note that the fundamental solution satisfiesCijkp, del 2, capital phi kr, over, del xj, del xp, equals, Kronecker delta ir, Dirac delta, x1 minus I1, x2 minus I2. The stress field corresponding to the fundamental solution, phi kr, x1, x2, xi1, xi2, is given by capital sigma ijr, x1, x2, xi1, xi2 equals 1 over 2 pi, real part of sum, alpha equals 1 to 3, Lij alpha, and alpha p, dpr, 1 over x1 minus I1 plus tau alpha, x2 minus I2. Together with a reciprocal relation, the fundamental solution may be used to derive boundary integral equations for two-dimensional elastostatic deformations of anisotropic materials in the absence of body force. We will derive here the reciprocal relation that will be used together with the fundamental solution to obtain boundary integral equations for two-dimensional elastostatic deformations of anisotropic materials. Let phi k, x1, x2, and psi k, x1, x2 be functions satisfyingCijkp, del 2, phi k, over, del xj, del xp, equals, fi, x1, x2. AndCijkp, del 2, psi k, over, del xj, del xp, equals, gi, x1, x2. In the two-dimensional region, R, bounded by a simple closed curve, del R. We multiply the first equation by psi r, and the second by phi r, take the difference between the two resulting equations, and contract the subscripts, I and r, in the resulting equation to obtain the scalar equation.Cijkp, psi I, del 2, phi k, over, del xj, del xp, minus,Cijkp, phi I, del 2, psi k, over, del xj, del xp equals, fi, psi I, minus, gi, phi I. Which can be rewritten as del over, del, xj, psi I,Cijkp, del phi k, over, del xp, minus, del over, del xj, phi I,Cijkp, del psi k, over, del xp equals, fi, psi I, minus, gi, phi I. Integrate the equation that we just derived, over the region R, to obtain double integral, over R, del over, del, xj, psi I,Cijkp, del phi k, over, del xp, minus, del over, del xj, phi I,Cijkp, del psi k, over, del xp. dA equals, double integral, over R, fi, psi I, minus, gi, phi I, dA. Applying the divergence theorem on the double integral on the left-hand side of the equation above, we obtain the reciprocal relation between phi k and psi k, given by line integral, del r, psi I,Cijkp, nj, del phi k, over, del xp, minus, phi I,Cijkp, nj, del psi k, over, del xp, ds equals, double integral, over r, fi, psi I, minus, gi, phi I, dA. Note that, ni, is the xi component of the unit normal vector to the boundary, del r pointing out of the region R, and ni may vary from point to point on del R. Consider the following boundary value problem for two-dimensional elastostatic deformations of anisotropic materials. Solve the system of elliptic partial differential equations.Cijkp, del 2, uk, over, del xj, del xp, equals 0, in R. Subject to the boundary conditions. UK equals VK x1, x2, 4, x1, x2 on C1. PK equals WK x1, x2, 4, x1, x2 on C2. Where R is a given two-dimensional region, which is bounded by a simple closed curve C, C1 and C2 are non-intersecting curves such that C equals C1 union C2, PK equals sigma kj and j, is the xk component of the traction on C, and j is the xj component of the outward unit normal vector on C, and vk and wk are suitably prescribed functions on C1 and C2 respectively. To apply the reciprocal relation to obtain a boundary integral solution for the boundary value problem, we let psi equals ui x1 x2 with gi equals 0 and phi equals capital phi ir x1 x2 psi 1 psi 2 with fi equals Kronecker delta ir Dirac delta x1 minus i1 x2 minus i2 for r equals 1, 2, 3. Note that capital phi ir is the fundamental solution of the elliptic partial differential equations for two-dimensional elastostatic deformations of anisotropic materials. We obtain the boundary integral equations. Lambda, xi1, xi2, ur, xi1, xi2 equals line integral over C, ui, x1, x2, capital gamma ir, x1, x2, xi1, xi2, minus, pi, x1, x2, capital phi ir, x1, x2, xi1, xi2, ds x1, x2. Note that, capital gamma ir, is the traction corresponding to the fundamental solution, capital phi ir, given by capital gamma ir, x1, x2, xi1, xi2 equals capital sigma ijr, x1, x2, xi1, xi2, nj, x1, x2. The parameter lambda, xi1, xi2, is given by lambda, xi1, xi2 equals double integral over r Dirac delta, x1 minus i1, x2 minus i2, dAx1, x2, which has the value 0 if the point xi1, xi2 lies outside R, 1 if the point xi1, xi2 lies inside R, and 1 over 2 if the point xi1, xi2 lies on a smooth part of C. We will now discretize the boundary integral equations to obtain a numerical procedure for solving the boundary value problem. Put n closely packed points on the boundary, C. Join two consecutive neighboring points to form n straight line elements denoted by C1, C2, and so on until C n minus 1 and C n. We make the following approximations. C approximately equals C1 union C2 union and so on union Cn minus 1 union Cn. UK approximately equals UK n and PK approximately equals PK n on the element Cn. UK n and PK n are constants given by the values of UK and PK, respectively at the midpoint of the element, Cn. The boundary integral equations are approximately given by lambda, xi1, xi2, ur, xi1, xi2 equals, sum, n equals 1 to capital N, ui, n, line integral over, Cn, capital gamma ir, x1, x2, xi1, xi2, ds x1, x2. Minus, pi, n, line integral over, C, n, capital phi IR, x1, x2, xi1, xi2, ds x1, x2. If UK, n, and PK, n are both known for n equals 1, 2, and so on until n, and if we know how to compute the line integrals over C, n, we can use the discretized boundary integral equations with lambda, xi1, xi2 equals 1 to compute UR at any point, xi1, xi2 in the solution domain. However, from the boundary conditions, we know either UK, n or PK, n, not both, for a given n. If we know UK, n, we do not know PK, n, or vice versa. Hence, the right-hand sides of the discretized boundary integral equations contain 3n unknown constants. We can set up a system of 3n linear algebraic equations to determine these unknown constants. We can collocate the discretized boundary integral equations by letting psi1, psi2 to be given by the midpoint psi1, m, psi2, m of the element C, m, to generate a system of 3n linear algebraic equations given by 1 over 2, UR, m equals, sum, n equals 1 to capital N, UI, n, line integral over, C, n, capital gamma IR, x1, x2, xi1, m, xi2, m, ds x1, x2. Minus, pi, n, line integral over, C, n, capital phi IR, x1, x2, xi1, m, xi2, m, ds x1, x2. 4, r equals 1, 2, 3, and m equals 1, 2, and so on until capital N. Note that lambda, xi1, m, xi2, m equals 1 over 2, since the midpoint, xi1, m, xi2, m, lies on a smooth part of C, m. Details on how the line integrals over C, n are computed are given in Clements and Rizzo 1978 and Clements 1981. The unknowns, either UK, m, or PK, m, whichever are not given by the boundary conditions, can be determined by solving the linear algebraic equations. If you find this video lesson useful, please show your support by liking this video, subscribing to the channel, Reciprocal.